Oh, am I too loud or quiet, or is this fine?
You're good.
Okay. Mic is like every once in a while it's like red. It's like, oh.
Hi, Todd.
Everybody.
Hey,
God.
We're waiting to see if our friends from last week show up.
Oh, I hope they show. Oh, they were recording. I shouldn't say anything.
hi Amanda. Nice to meet you.
Hi, Amanda. Yeah.
Hi, Amanda.
Hi. Oh, Todd. Hi. Nice to meet you. Everyone, I know Todd. We've known each other a while. Nice to be here.
Hi.
This is great. Yeah, I'm happy with the turnout so far. I hope that a few more people maybe join in the next couple of minutes and then we'll get started.
I'm gonna go get my dog. I'll just hold on a second.
Gwen's dog also programs in R.
Yeah.
Yeah. Okay.
Thought it was
First.
R.
Is the world's best rubber duck.
Hi Robert, by the way. I see you.
Heyo, how are you?
Good.
Good, I'm glad.
Yes.
She wants to say hi. You want to say hi to everyone?
Hello.
She says hello.
Puppy.
She's really looking forward to learning about asynchronous programming and Plumber.
We all are. All right. I mean, I don't think there's too much use in dilly-dallying. So whenever you want to get started, I feel like we're probably good to go.
Awesome. Exciting. Awesome. This is a, close group. I like this. So, okay. Hi, everyone. My name is Barret Schloerke. I am at RStudio. I am one of the lead developers on Plumber, and it's great having you here today. I'm really excited about today. Last week is like setup, routine. We got to get through it. But like today is where we get to play. And so I have a little bit of slides from a prior presentation, but I think today's going to be more hands-on, and we're going to work through things together in code. So if it gets a little messy, sorry, but it's fun to try. And I think we need to do that because it gets complicated quickly. But it's neat to touch it yourself, touch the code yourself. Okay, so let's see if I can share screen. And then I think when I present, all my monitors go away, and so I cannot see anything. So we'll just hope things go well for a little bit. All right, so play. Oh, good, I can still see you guys. This is great. Let me get my mouse back. Can't see anything. Perfect. And one last try. Great. Okay, I got my mouse back, and you guys have bigger faces. Perfect. Okay, so last time, Plumber, we can make our routes, and we can make an API. I think we should be familiar with that and comfortable with that. Anyone not familiar, please speak up now, and we can take 5 minutes. Don't see any head shakes, so okay, cool. All right, so we have a route, and this is going to be an API, and we have two routes. We have a fast route and a slow route. And for practical purposes, the fast calculation just does like 1 + 1, and the slow calculation does system sleep for 10 seconds and then returns 1 + 1. Like, we can just think of it that way. You can insert like calculate complex model, or do something that takes a lot of time. That's just a differentiator, something that's like instantaneous versus something that is not. The ID that we have in there is something that I just use for a submission order. So in the code, it just doesn't really do anything in my examples, but we can see if I say fast 1 and then fast 2, it was submitted first with fast 1 and then with fast 2, and that way we can keep submission order consistent, even though things may finish in a different order. Okay, so if I was to submit some requests to this API, click back here, great. There's kind of 3 main stages. There's that like Plumber does per API request. There's the part where we like deconstruct all the parameters and the post body requests, things like that, whatever. It's in the receive stage. Once we have those parameters all set up, we can then process that, and that's where your Plumber function like kicks in that you provided, like fast calc or slow calc. And then when that's all done, we then serialize that all up, and we can do that with JSON or YAML or Feather, whatever you'd like, and that's in the response stage, and then it's sent out the window. And Plumber is in R, and so things are done serially. So 1, 2, 3, and only one item can be working at a time. That is kind of the definition of what R is. Okay, so if we had an example where we did a fast request, then a slow, then another slow, and a fast request, it would look something like this. So the fast request comes in, it processes really quickly, it responds, and it's done. A slow request comes in, it's processed super slowly, and it takes a lot of time. And we're still holding on to it. Nothing else can be there, even though we have 2 requests waiting. It's responded done. A slow 3 comes in, and it's also going to take a long time to process. It's painstaking long because models take a while, no big deal, but they do. And then, okay, now we're done. We can respond really quickly. And then the fast request comes in, it processes and responds. And we can also think of a fast request as like an echo route or like a status route, like, am I alive? Yes or no? We want those to respond instantly. In that demo, they took like 30 seconds, and that's a little terrifying when you're doing an echo route or a status route. So if we were to look at this requests on paper, this is what it would look like for execution time. So they all arrive one after each other, and so the fast route immediately is handled and executed and responded. Then the slow 2 is picked up right away, and it works for 10 seconds. Great, perfect, amount of execution there. But slow 3, we have this dotted line here where it's waiting, and it waits 10 full seconds, and there's nothing we can do about it because R is serial, and that's bad. And then finally, fast 4 had to wait 20 seconds to execute, even though it's only going to work for instantaneous, but it had to wait because that's the order that the requests came in. So that area right there is opportunity or really bad, however you want to look at it. I would like to get rid of it. Okay, so here's our Plumber code, and those red bars of wait time can be addressed if we were to use another package called Future. So Future is a package, and we'll play with this a little bit later, but Future is a package that allows you to execute code on a different, I'll call it an R worker. It's not necessarily another core because your computer can make decisions of its own, but we'll call it an R worker. And that way, if you have Gwen's machine that we talked about last week where it had, 32 cores? Did you have, Gwen? Something huge, right? We'll say it's 32 cores. Right now, Plumber is typically only on 1, and you only have 1 process to work with. But if you have 32 processors, it would be great to leverage all of them. And so Future allows you to offload that work into that a different R worker, which is independent from your main R session. And the code change that is required is basically 2 lines. One is the initialization line. You need to tell Future how you want your Future code to be executed. In this case, we're going to do a multi-session. So it's a completely different R session. You can do things like fork if you want to do better memory management, possibly. There's different options, but I like multi-session for getting your feet wet. The other part is, now that we've initialized future, is we need to tell future, hey, go run this code. And it's not much like addition to just say future, or if you library the package, you can just say future parentheses, and then you give it an expression. This expression, future will actually inspect and look for and see that, hey, I need the slow calc function, I need the ID variable, and possibly other things. And it will go and capture that and then send it to the extra R worker. That is a lot of bit of magic, and I think it's really cool how it does it. But we can just kind of say Plumber is really smart and it does some voodoo, future is really smart, does some voodoo, and then just handles that for you. So that code in slow calc will actually execute in another R process. That's a crazy idea for adding one line of code. So just those 2 lines. So here's what it was before with just Plumber, just standard R code. And then now if we enable future by wrapping around slow calc and setting the plan, we can actually get slow 2 and slow 3 to execute concurrently. And then since nothing is blocking on the main R thread, fast 4 can go right away. And now we have no waiting time, and this is as optimal as it gets. Yeah, save all that time, save all that time. Yes. Okay, so Plumber, main R session. We still have our receive, process, and respond. If we add in 2 future workers for this example, we now have these guys, and we're only going to be using them in the process step. You technically can use them in the receive and respond, but for practical purposes, we're just going to talk about the processing step. And so we can actually change those slow routes to work on future like we were doing, and this is what it would look like. So fast comes in, processes in the main R worker, and then finishes. Great. Slow comes in, is offloaded to worker 1, begins. Slow 3 comes in, offloaded to worker 2. Fast 4 is not blocked on the main R thread or R session and can continue through. Slow 2 finishes, it responds. Slow 3 finishes and responds. Yes, got it. I think that is a lot of it's kind of like, ooh, I got a new trick. I got a new trick in my arsenal. I can offload things with future, just like, oh, it's a slow route, wrap in future, everything else will be faster as long as you have enough traffic. And that's how we can get that fast 4, because it's not blocked by that main R session.
So you have to identify what makes it slow, though. Is that right, Barret?
That's correct.
Identify. Is there like a rule that helps you know if it's a slow or fast one?
Yes, actually. So let me get this up here. So second bullet, future isn't instant. It takes like a quarter of a second, we'll say, to do the communication. I know it's probably faster than that, but we'll just say it's a quarter of a second. So if a quarter of a second means a lot to you in your execution time, then maybe don't use future. But if a quarter of a second doesn't mean a lot to you and you can wait 3 seconds or something, then sure, offload it to future. And then that 3 seconds of calculation is done on a different R session. But there is a cost to the communicating between the 2 different R workers. Yeah, so that's why you have to manually add it. Otherwise, I would personally just who is it? Yeah. Oh man, brain fart. Um, RServe. Yeah, RServe does everything asynchronous. Every route is in its own process. Um, and so they've done a really good job optimizing up front, and then each route is executed serially, but each request is in parallel. Where Plumber, the whole kit is in the main R session, and then will offload to a worker where necessary. So they can do some better bandwidth, possibly, especially when the server is set up properly. I've seen those benchmarks, but either way, like being able to just declare this one is in parallel. Positive side, Future will allow you to declare, oh, run this on a different cluster. Like you can set things up like that. So even though I'm on my local machine, I can actually spawn a request to a cluster on a separate server. I think that's really nice. Yeah, so it's kind of fun. So you have to manually add your future calls, and it's not instant. And you have to balance processing power and memory size. So let's think about like my personal machine. Let's imagine I have 16 gigs of RAM, and I'm calculating a model that takes 1 gigabyte of RAM to do in an R session. If I'm sitting there and I'm wanting Plumber to at least have a gigabyte of RAM itself, I would kind of say you should have no more than 16 workers. Because if you do that, your RAM will start to balloon too heavy, and like you're going to start paging memory in and out, and that is now slower. If I had 15 workers, but my processor it's not doing like RAM heavy, but like we're looking at our processors, like you can kind of think 1-to-1 or maybe like 1-to-2. So I have 8 cores, 16, 15 processes. I know it's not bad, especially there's some setup and overhead from there. I think if you're doing like things like database calls and things like that, you could probably get away with 3x. Like you could have 3 times the amount of workers as you do cores on your machine. But you don't have infinite, and that's the important part. Yeah, your computer will come to a crawling halt very quickly. That's awesome. Do you have any more questions, Gwen, or anyone else? No? Turn my fan on here. Okay, good. Yeah, so here was that part on the far right. The can, like Plumber can invoke future, and future can parallel process R. So it's like, we're gonna fill in this part next week, promise. Okay. So one of the questions that came up when I was working with the setting up future within Plumber is, what happens when I run out of future workers? So I was like, oh, piece of cake. You know, if you have 10 workers, like it'll just kind of offload it and no problem. Like let's say we have 10 workers and we have 20. Shocking to me. I was not expecting that. Slow, 6, done. Whew. So I kind of sat there and this is what the time looks like, without the animations. And there's a lot of dashed lines in there. During this whole time section from 0 to 20 seconds, because there was more API requests that wanted to use a future worker than there were future workers available, then this section of time was blocked. And you might kind of go like, oh, well, it's not that bad. Like, still the work is done. The only one that really suffered was fast 7. But you could argue that slow 1 and slow 2 didn't get to respond when they wanted to. This is a toy example with just 6 requests, but what if you had 100 requests? Then we wouldn't be able to respond until the 98th time slot. that would be a very long time to wait. Hey, Todd.
Hey, Barrett, thanks for calling me. So just to clarify something, slow 1 and slow 2 didn't actually respond until time 20 seconds.
Correct.
And because they were blocked, I missed how they got blocked and why they didn't complete execution, even though slow 3 was blocked at the beginning. I missed that part. Is that just part of the way future works? That when there's an overloaded scenario, an oversubscribed scenario?
Correct. Yes.
Okay.
Future will say if no worker is available, it just sits with while true until a worker does become available.
So slow 3 is blocked, waiting for slow 1 to finish. Slow 1 finishes, and it goes into the response promise queue. Then slow 3 starts. How come slow 1 didn't get responded to at that stage?
So maybe I have a mislabeled diagram, but we could think the top left is like already queued in the main R thread. And so it has priority over this purple queue. So the top left group must be processed or handled before this purple promise queue can be executed.
Wow. That seems, I don't know. Okay.
I agree. And so but it's in the code, it's in the README. And it's a rare occurrence for the most part. But when it does happen, it's all over the fan. So yeah. So it's blocked there, and it's blocked at the very last sliver of 30. But we do have this nice gap between 20 and 30 where we could do other things like, a counter or something that's invalidating in Shiny or something like that. And so to remedy this situation of being blocked while we have more work to do than we have workers available, I made a new function called future promise inside the promises package, and it should be a drop-in replacement wherever you use future, but instead it's from the promises package. The benefit of this is that what I do is I create a promise to execute your code in the future using future. And I think it's best explained with this picture, in that the waiting time at the end has been removed, and also fast 7 has been moved to the beginning because we're not going to be blocking the main R session. And also slow 1 and slow 2 are not waiting to respond. The blocked amount of time within your R session is only at like the 0 mark, the 10 mark, 20 and 30 when we are like deserializing or serializing the response. And that has to be there, but there's a lot of free time in between, which I think is great. It allows your R session to do more work, or you can shuffle in other asynchronous code. It's really nice that way. So let's actually see how it works. And it's now purple to say that it's using the future promise and not a future call. And the way that it'll work is a worker is available, great, we offload it. Worker is available, we offload it. Slow 3, worker is not available, let's hold it in a promise queue. Promise queues are quick, easy to do in R, and then we can put them all there. And then this allows fast 7 to finally execute through, which is what I was originally expecting before doing this project. And then, hey, slow 1 is done, slow 3 moves in, and now we just get expected future work behavior. Where if a worker is available, then one of the promises will be sent over. Yeah, animation was a little off with the promise queue there, but you get the idea. Yeah, so if you're ever using future, it should actually be promises future promise. And that's good for Shiny applications and for Plumber applications. And you could argue for other applications as long as you're expecting a promise as your response and not a future execution. Whew. Okay, that's the end for formal slides. Let me move you guys over here. That does not work. Is there any questions around future or anything like that? No. Cool. All right, so let's look at Gwen's question a little bit more about how do I know when a function is slow. And one of the examples that I like to do is Fibonacci sequence, calculate it using recursion. And Fibonacci is a good example because we're familiar with it, we can do it, and it's not too much code, but we can easily make it slow by calculating a bigger number. So if n is less than 1, return 1. Otherwise, fib of n minus 1 and plus fib of n minus 2. Great. If we run that, we have Fibonacci, and let's actually switch up my layout. Console. Great. Apply. Okay, great. All right, so we have Fibonacci up there. And if we do, what is it, fib of 10, it's 89. Oh. Okay, I was close. So Fibonacci, it could be off by 1, but the idea is there. If we actually do what is it, fib of 30. Ooh, this code's taking a while. Fib of 32. Oh, it's really starting to take some time. And it's hard for us as our users, we're hey, where's this code at? And so we can profile code, and I strongly recommend using a profiler because I believe I know where code is slow, and I'm still wrong today many times. And yeah, it's use a profiler. And all right, so if we do prof viz, and you provide an expression, we could do fib of 9. It may not get it because this is too fast. Yep. But if we do something a little bit slower, like 32.
Barrett, I got in an argument with the Stan people once about profiling code, and they didn't like to profile it this way because they said that because it only does it once, and they felt like you needed to do it several times in order to get. I mean,
True.
what would you say to them? I told them we'll just run it several times, write a function and run it several times if they wanted to. What would you say?
So they are correct in that if their goal is to look at optimization, then I strongly recommend something like micro benchmark. So we could do micro benchmark. What is it?
Yeah, that was what they were saying I should do, but I was but then you don't really know where it gets stuck, do you?
Yes, so you're asking two different questions.
Right.
So using micro benchmark, you're saying, does fib of 32 calculate efficiently? Yes or no? And it's how fast does that take? Where prof is, what it will do is it'll actually show you the line of code that is taking a long time. And I think that's pretty powerful. Because most likely you've written more than 5 or 6 lines. So let's actually make something a little bit easier to see in the profiler of fib slow. And what this will do is say sys dot sleep of 1 second, and not fib, but we need to recurse on itself, right? So let's do fib slow and fib slow, not of 32 because we'd never finish. Let's say like 5. No. 4. Great. Okay, cool. Yeah, so micro benchmark is great if your function is fast-ish and you're worrying about becoming faster. My case that I'm looking at right now is what about if your code is slow and you want to kind of make it like not as slow? And Profiz is really good for that. So you can hopefully find, they don't have it. Let's try it one more time. Let's put this code inside. Okay, so if I run it, try one more time. When you have an R package, I believe it does help a little bit more because it'll load that environment. There we go. So we can see fib slow went from 0 to 30 milliseconds? No way. Wow, this is really weird because we saw it take a lot longer. Funny. Maybe the syssleep caught it off guard. What should we do? There is, well, this example is backfiring. Trying to think of something that takes a long time. Oh, we could do the old fib 28 inside the fib slow. Maybe that'll show up as like slow calculations. Cool. So this flame graph is really handy to show you that, like, hey, you're doing a lot of call stacks here. Fib slow took 6,000 milliseconds. This fib 28 is actually where the time was taken, and also this recursive call is also slow. We can't see like which one it is, but you can see that there's a lot of time taken. We don't need to worry about this if statement because there's no time even recorded for this if statement. Right. So that's how we can kind of look at it. Going back to the a rule of thumb, if a quarter of a second doesn't make too much difference, then absolutely use a future promise in your route. But if a quarter of a second does make a big difference, like you're just doing 1 + 1, then I would not use a future promise. Cool. I also want to point out, sometimes it is, R is known for not being the fastest language, but I would also argue that most likely the algorithm that you're using is not the fastest. So if we were to do Fibonacci again, we can still do it recursively, but we can alter it a little bit. So I like to use a package called Memoize. One of the things with Fibonacci sequence calculation is if I plug in fib of 28, it'll equal fib of 28 today, tomorrow, yesterday, doesn't matter. It's consistent. And so I can leverage caching. And there is a package called Memoize and has a nice function called Memoize where you can cache a function's execution. So if you have consistent inputs to outputs, then it will say, oh, I've seen these inputs before. Here's the answer. So the way we can do it, Memoize of function of n copy this here, take out the slow part, and fib, not slow, because that would be bad, but fib mem, and fib mem. Cool. All right, so if we have this, we can do fib mem of, what is it, 9, should get 89, great. And if we do fib mem of, oops, there we go, fib mem of what, 30, last time it took some tangible amount of time, instant. Last time, what if we did, so what's the, like, for all the complexity nerds, Fibonacci doing recursively is what, 2 to the nth? So we could think the complexity is calculating a lot of things. This function, because it's being cached, only needs to calculate the numbers once. So it's not like, so fib mem of n will need n calculations rather than 2 to the nth calculations. And so we can actually calculate fib mem of 300, no problem. And if we were to do that with a regular recursive function, that would, you can go home and retire before it finishes. So yeah, sometimes we can just adjust our algorithms a little bit and they'll execute much more efficiently. Just want to throw that out there, that R is not necessarily always slow.
Mm. Mm. Mm.
Okay, so let's bounce back and look at some just like live examples of a running Plumber process where things are happening. Let's actually, let's pull up. Great. So let's do share screen. Okay, so let's look at, let's run this guy. Plumber, plum, where is this? Oh man. There we go. Paste. Great. Okay, so have a Plumber API open, and I'm running it on 8080. I know we can do things through Swagger, but I think this is a little bit more useful looking at it in the browser. There's 2 routes. One where we, let's look at this one first. One where we had our fast calc and we have our slow calc. So fast is going to return great, and slow is going to block for 10 seconds, 5 seconds, something like that. So let's actually run this one, copy path instead. Great. Copy. And we want to go /sync. And is that an error? No. Great. And if I actually, so you can see that one took, a fair amount of time. Let's refresh this. Maybe I'll copy it into a new tab. So it's been submitted. 3, 4, 5, 6, 7, 8. Yeah, 8 seconds. And if we actually load up 3 more tabs, they'll all go synchronously. Like this is people coming to your website and they're wanting to run their models one after another. They're all submitted at the same time, expecting 8-second turnaround, but only the first one took 8 seconds. This one's going to respond within 16, and then this one will respond within 24 seconds. So bad. That's bad. Let's instead look at similar code, but what we've done is we've taken our our slow code and wrapped it in a future. So let's copy path. Great. We have the fast and slow. So we could actually do like slow 3, slow 2, slow. Close that, sync. So even though this guy, let's reset here. So I'm going to refresh this one, the first, second, and third, and then now that we've been offloading them with futures, the synchronous should be able to execute right away. So we'll go refresh, refresh, refresh. They're all working. I can refresh the fast, and it doesn't respond right away. Well, it responded faster than the other two, so that was good. So still, I think we ran out of workers, right? Did I? Yeah, I only had 2 workers. I ran into my own bug. Yeah. So, and to prove that it's working on a different process, I'm gonna switch up the routes to return, like sync just returns the system time and the git PID, the PID, the process ID. So if they're all running on the same process, they would return the same number. But if they're working on a different worker, you can actually see a different PID, which is like something that Linux users would be familiar with. So let's cancel this one, copy path, and sync and future. So let me switch these up to so sync responded immediately. Great. Has process ID 68959. The first future responded with a PID of 8,678. 8,678. And this one, I'm going to guess is going to be 8,678. So it looked like they're only using 1 worker. But it's not the main R session, and that's the important part. So at least you can offload it, keep your echo route or your status route or some lightweight routes to respond immediately. Yeah. So we have a little bit of time. Is there any questions? Or I know I'm kind of sprinting through this, but I just want to like open your eyes to what's possible and let you go, Oh, cool. What's that? And then we can read things up later. But is there anything I can dive into deeper or answer any questions?
I have one question that was like occurring to me as we were thinking about all of these like slow processes and spawning them off on future workers, which is like is there integration for this like if I wanted to dispatch something to like I know dbplyr is out there to work with like databases that you can connect to through R, like maybe that's kind of a slow process that I'd want to be asynchronous. Or like alternatively, maybe I have like compiled binary executables that I like kind of want to make a system call to. With future, is your only option spinning up another R session to make like those calls from? Or like are you always going to have the overhead of another R session, even if you maybe don't actually need to boot up that other R session to do anything asynchronously in R or with Plumber?
Um, the way, I mean, if you're going to do something in a different call, you could just do a system call if that was your goal. Like you could just say system to or system and say wait is false, and then you're fine.
Right.
Your route would want to finish, but in this case, if you're doing like dbplyr, if we were to do dbplyr, I would do something like con is make connection inside the future process, because sharing connections between our process is gets a little fussy. So I would just recreate the connection, because again, a quarter of a second doesn't make that much time difference. And then you could do your dbplyr commands here, and then return dbplyr result. And then we would just get rid of all this, and that's it. So we would just move this block of code inside that future call. If you're worried about the R overhead, I would possibly look into doing like a different session. So there's multi-process. I think multi-core just got removed. But he on the future website, he goes into like the advantages of them. And one of them would be a fork-based process. They're faster because it's much better than like forking an R process in Linux is fast. But there are some disadvantages, like your connections are now like in two spots. And if you use a fork I think it's multi-fork maybe, plan inside the RStudio IDE, gets mad because it's there's like some WebSockets in there, and it wants to share the WebSocket in two locations, and so it gets confused. But if you have your own like quiet Linux server sitting somewhere, then it might be really nice to do. Because you're not spinning it, you're just kind of cloning and then working and then returning an answer.
It's been a while since I've thought about like forking processes and stuff like that, especially like in a Linux environment. So is when you fork like an R session like that, does all of your memory get duplicated, like everything that you have loaded up in R? Because that sounds really costly, but at the same time, I hear what you're saying, like, well, forking a process is faster. So maybe that's, if you had to do something really high speed, maybe you'd want a different like processor format declaration for future. So I'm trying to reconcile the two ideas.
Correct. So if you had a very big data set and you're passing it by memory, that would possibly be very bad. If I believe, don't quote me on this, but I believe the advantage for using a forked R process is memory is only duplicated on write. So you can read from the same location, but once it gets altered somewhere in either one, then it's written. So that's an advantage for a forked R process, I believe. So it's like copy on write. Yeah. I could be wrong, but for my usage, I've just done general independent R session that you send a message to. And if you can minimize that communication, you just say like, oh, load data set 2. And then inside that process, you do heavy data reading. Like then the communication is just a little 2, not a book of information.
Thank you.
Any questions, Todd?
I've got so many questions. There's not enough time to go over all of them. No, this is amazing, Barret. Thank you so much for this. I guess this was really helpful. I'm not going to use this right now, but to know that it's possible and how this works is exceedingly helpful when the time comes. I think that it's unfortunately inefficient.
Yes.
So considering you work at R, what are the long-term, I mean, this is being recorded, so you don't have to answer this question. What are the long-term goals to address what is arguably one of the most fundamental criticisms of the programming language compared to Python?
For speed?
For everything that you were talking, yeah, speed, threading, performance, all of this stuff. These are, when if you're trying to recruit somebody into your, I don't know what the right word is, language, so to speak, this is a long-term concern.
That's fair.
Or maybe not. Maybe it's not fair. I mean, again, different.
No, it is. So if you're looking at it for a production standpoint, I agree that my current understanding is Python's does have thread support, so you don't need to launch a full separate process, but it can kind of bounce back and forth. R has tried to do something similar with using promises and later, so you can do like later, and that's like making a JavaScript promise. And it's really weird where you can have like 1 plus, like you say later, print hello, and then you say 1 plus 1 and you run it, and 1 plus 1 shows up, and then randomly message hello appears afterwards. Like creepy, but it works. And that's like the foundation of Shiny and Plumber.
Mm-hmm.
But I agree
sorting
that
through those asynchronous responses is always a problem. I mean, like,
yes,
non-uniform. Yeah, it's a big problem.
It's a big problem. But I think JJ hit it on the head, saying that R as a language is a human language. So it should be the interface that you use, and you should want to write in it, even though we may offload it. Like as he does with Keras, it's actually executing inside Python. Or if you want to use TensorFlow, but the interface is through R. And I think that's the important part.
Awesome, thank you.
So my advisor, Bill Cleveland, he, grad school advisor, he would always say that we as developers or humans are very expensive. So our time is very important, and we need to minimize the friction and overhead for that. And so even if the algorithm takes 30 seconds longer, but I can get there 2 hours faster, then I can do so much more work down the road. And it's fun to do that exercise where you can write your R code with a for loop, you can then write it with an lapply, and you can see that it's 10 times faster, and then you can write it again in C, and you can see it's 100 times faster than that. But how long did it take you to do all those things? And if you wrote it in C, it's 20 times more costly to write it.
That is absolutely correct. There's no argument there. The only issue is about going from that stage to a fully operational production environment. And that's the gap. So if I were to go to, like, I'm dealing with this with hey, can we do this? And the answer is no, we cannot do this in R. I'm surrounded. I was joking the other last week. I'm like, I'm surrounded by Python people. Exactly. So I'm not getting past that. Yeah.
Yes. Yeah. If your team is Python, then you should leverage that.
No,
not
it's just
gonna-
means well, this is being recorded, but yeah, I'm screwed. There's nothing I can do. So.
Yeah.
Thank
This
you,
is
Barret.
the
This is amazing.
Py2R. Yeah.
I have a
Once.
sneaky
yeah,
question,
sure.
which is like, are there upcoming things you're working on that you want to tell us about, or you know, are there things to expect coming out? But you know, don't share anything that you're not supposed to share, or do. But
With Plumber, I think I answered that one last week with I'd like to have middleware so that we can have like authentication different per route and it's not clunky to do. Right now, it's very, if you want to have like the home route versus like the user route to have different authentication requirements, it's difficult to achieve. I'd like that to be much simpler. So middleware would be great, and then also similar to like the Python decorators, I'd like to have custom decorators in Plumber. Right now, it's a very fixed set, and people can't do what they want custom ones, and instead it'd be a lot nicer to be like the @Barret tag, and that is something special that I can do to the route. And you know that kind of goes with middleware where you can say like add auth, and you know we have information to pass into the authentication stuff. So both of those would be wonderful. I'd like to have those. I don't know when it's going to happen. Focus is in other places.
that sounds awesome.
Well, thank you for having me today. I appreciate it. It's been fun to walk through all these with you. Thank you for your time.
Thanks, Barret.
Thank you, everyone.
Have a great night.
Yeah, thank you for having
Thank you
us.
so much.
Thank you.
Welcome. Welcome. Cool.